Hello everyone. This week we will discuss the simplest hydrocarbons, the alkanes. In Module 9, you were introduced to the first 10 alkanes. Alkanes are the simplest hydrocarbon group. They are made up of a string of carbon atoms covalently bonded to hydrogen atoms. All the carbon atoms are bonded to hydrogen atoms using single bonds. Thus, alkanes are called saturated hydrocarbons. The general formula for alkanes is CnH2n plus 2. For example, if octane has 8 carbon atoms, how many hydrogen atoms does it have? Using the general formula, we multiply 8 by 2, then add 2. So, the molecular formula for octane is C8H18. Alkanes range in size from 1 carbon atom, as in methane, to more than 50 carbon atoms. Their basic structure is made up of a string of CH2 groups flanked by a methyl group at both ends. Alkanes differ only in the number of CH2 units within the bonds. These CH2 units are also called the methylene group. Substances that differ by a constant unit are said to form a homologous series. So, alkanes are homologous series of CH2 or methylene groups. Substances with the same homologous series have similar chemical and physical properties. Methane is the simplest alkane. It is the main component of natural gas. The smallest alkanes, those from 1 carbon up to 18 carbon atoms, are primarily used as solvents and sources of energy. Alkanes are nonpolar, water-insoluble compounds with relatively low melting points and boiling points. This table shows the physical properties of the first 10 alkanes. Notice that the first 4 alkanes exist in the gaseous stage. They also have very low boiling points, which make them ideal sources of energy. The next group of alkanes are in liquid form and make them ideal solvents. In the previous module, we covered the naming of organic compounds. Many organic compounds have alkanes as the parent chain, but alkanes can also become side chains. When this happens, alkanes are referred to as the alkyl group. When naming alkyl groups, we simply change the suffix of the alkane from -ane to -il. For example, methane becomes methyl. Not all alkanes form side chains. Only the small-numbered alkanes do so. Let's go over the first 4 alkyl groups. As stated earlier, when methane becomes a side chain, its name changes to methyl. The structural formula of an alkyl group is the same as the alkane minus 1 hydrogen atom. The last column of this table shows the line structures of each alkyl group. You should become familiar with these line structures as they will be used in the exam. Just remember that each corner or bend represents a carbon atom and the line represents a bond between them. Note that propane has 2 versions of its alkyl group, propyl and isopropyl. These 2 forms differ in how the carbons are bonded to each other. They are also named differently. Here we have butane and its 4 forms of alkyl groups. These forms also differ in the way the carbon atoms are arranged together. Although the molecular formula of these 4 forms are the same, their arrangements are different. In butyl, the methyl and methylene groups are arranged in a straight chain. In isobutyl, one methyl group is attached to the central carbon in the chain. In sec-butyl, the methyl and methylene groups form a straight chain, like butyl, but the attachment to the parent chain is in the second carbon, not the first. In tert-butyl, the four carbons are arranged to form a tetrahedral shape with the parent chain. What does the sec in sec-butyl and the tert in tert-butyl mean? A carbon atom in a hydrocarbon chain can be designated as primary, secondary, tertiary, and quaternary based on how many other carbons it is attached to. Primary carbons are attached to only one other carbon. The first and last carbon atoms in a chain are usually primary carbons. A secondary carbon is attached to two other carbons. A tertiary carbon is attached to three other carbons, and a quaternary carbon is attached to four other carbons. Designating carbons in this manner allows us to know easily how an organic compound is structured. So the sec in sec-butyl is short for secondary because the carbon attached to the parent chain is attached to two other carbons. Tert is short for tertiary because the carbon attached to the parent chain is attached to three other carbons. Okay, let's try naming this alkane with two alkyl groups attached. First, we need to find the longest continuous chain of carbon and name it. We can number the carbons from right to left as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We can actually go down this way and number this as 8, 9, or 10, or even this one as 10. Either way, we have 10 carbons as our LCC. So, the name of this parent chain is decane. Now, if we consider going from right to left, we have two alkyl groups attached. This one has one carbon, so it is methyl. This alkyl group has 1, 2, 3, and 4 carbons, so it is a butyl. However, it is not a straight chain butyl but an isobutyl. This isobutyl is attached to carbon 7. This methyl is attached to carbon 2. We numbered it from right to left because according to the IUPAC rules, we number from the side nearest a side chain. So in this case, this is nearest to the edge compared to isobutyl. So we can name this compound by arranging the side chains in alphabetical order. We have 7 isobutyl, 2 methyl decane. However, as I said earlier, there is another way to name this compound. If we go down this way and end here, we would have two other side chains. This one has one carbon, so this is methyl. And then we have this side chain which has 1, 2, 3 carbons, so it is propyl. And it is attached to carbon 7. This methyl is attached to carbon 9. So another way of naming this compound would be 2,9-dimethyl 7-propyl decane. Both of these names are correct. These two structures are actually isomers. We will discuss isomers later. Alkanes undergo very few reactions, but the two most important ones will be discussed here. The first one is combustion. Alkanes undergo an oxidation reaction called combustion, wherein it reacts with oxygen to produce carbon dioxide and water. The energy released in this reaction is the reason why alkanes are used as energy sources. Halogenation is a reaction involving the removal of a hydrogen atom from the alkane to be replaced by a halogen. In this example, propane reacts with chlorine gas to produce 1-chloropropane and hydrogen chloride. However, this is not the only possible product of the reaction. In some cases, 2-chloropropane is produced. 1-chloropropane and 2-chloropropane differ only in the attachment of the chlorine atom to propane. These two products of the reaction have the same molecular formula, but they differ in their attachment of the chlorine atom. They are called isomers. We will discuss isomers later on. Now let's go to a special group of alkanes called cycloalkanes. Alkanes do not just exist as straight-chain hydrocarbons. In some instances, they can form cyclic or ring structures called alicyclic structures. Cycloalkanes occur for alkanes with at least 3 carbon atoms. It involves the joining of the two ends of the straight chain to form a ring. In the process, 2 hydrogen atoms are removed. The general formula for cycloalkanes is CnH2n. Naming cycloalkanes is similar to naming alkanes. We simply attach the prefix cyclo to the name of the alkane. So for example, a 3-carbon ring is called cyclopropane, and a 6-carbon ring is called cyclohexane. Each corner in this ring represents a carbon atom, and the lines between them represents the bond. Here are examples of cycloalkanes, from cyclopropane to cyclodecane. You should become familiar with the shapes of these cycloalkanes. If you are already familiar with Greek prefixes, then you should be familiar with the shapes they are referring to. For example, cyclohexane can be represented by a hexagon, and cyclooctane can be represented by an octagon line structure. Now let's practice naming cycloalkanes. The first step is to determine the parent chain. The cycloalkane is the parent chain if it has more carbons than a straight chain alkane it is attached to. So in the first structure, we have here a cycloalkane that has 1, 2, 3, 4, 5, 6 carbons. It is attached to a straight chain alkane that has 1, 2, 3 carbons. So in this case, the parent chain is the cycloalkane, and since it has 6 carbons, we name it cyclohexane. Now let's go over to the other structure. It is a cycloalkane with 1, 2, 3, 4 carbons. It has a straight chain alkane attached to it that has 2 carbons and another one that has 1 carbon. So the parent chain is the cycloalkane. Since it has 4 carbons, we name it as cyclobutane. Now the next step is to identify the side chains. If there are 2 or more side chains, we number the carbons of the parent ring to which the side chains are attached in such a way that the sum of the numbers is the lowest possible. If there is only one side chain attached, there is no need to number the carbon in the parent ring, since it is understood that wherever the side chain is attached, the carbon on the parent chain is numbered 1. So in our first structure, we have one side chain here that has 3 carbons. In our second structure, we have 2 side chains here. One has 2 carbons and the other 1. Okay? As the rule states, we do not have to number this carbon because it is understood to be 1 because there's only one side chain attached. However, in this second structure, we need to number the carbons because there are 2 side chains attached. Do we number clockwise or counterclockwise? According to the rule, the sum of the numbers must be the lowest possible. So, if we number this counterclockwise, this would be numbered 1, this would be 2, 3, and 4. So, if we add 1 and 2, it would give us 3. However, if we number this clockwise, as in 1, 2, 3, and 4, our side chains would be attached to carbon 1 and 4, which gives us 5. Since 3 is a lower number, our numbering is counterclockwise. So going back to the first structure, this is a 3 carbon side chain. So our side chain is named propyl. However, if you recall, there are 2 forms of propyl depending on which carbon is attached to the parent chain. In this case, it is the middle carbon, so this is isopropyl. This next structure has 2 side chains. The first one is 1-ethyl. The other one is 2-methyl. Remember that in the system of nomenclature, side chains are arranged alphabetically. So 1-ethyl comes first, whereas 2-methyl comes next. So now we name the side chains and place them in alphabetical order. In our first structure, we only have one side chain, so we write here isopropyl. Attach it to the parent chain name, cyclohexane. In this other structure, we have 1-ethyl, which comes before 2-methyl, and the parent name is cyclobutane. So our first structure is isopropyl cyclohexane, and the other structure is 1-ethyl 2-methyl cyclobutane. Let's try naming these 2 cycloalkanes. Our first structure has a cycloalkane with 3 carbons. It is attached to a straight chain alkane with 2 carbons and to 2 other straight chain alkanes with 1 carbon each. Since our cycloalkane has more carbons, it is our parent chain. A 3-carbon cycloalkane is called cyclopropane. Now, because we have more than one side chains, we have to number the carbons in the parent chain. Remember, our numbering is alphabetical. So since this side chain is ethyl and these two are methyl, we number ethyl carbon as 1 and this one as 2, this one as 3. Our numbering is counterclockwise because it gives us a lower sum than if we numbered it clockwise. So we name our side chains as 1 ethyl. Okay. Now since we have 2 methyl groups attached to carbon number 2, we have to write number 2 as many times as there are alkyl groups attached. And remember, if there are 2 methyl groups attached, we have to use their prefix indicating how many methyl groups there are. In this case, we use di. So this structure is called 1-ethyl 2,2-dimethyl cyclopropane. Now let's go over to the other structure. This cycloalkane has 1, 2, 3, 4, 5, 6, 7, 8. So an 8-carbon cycloalkane is cyclooctane. So now we have to number our carbons. Do we number starting with bromine or with iodine? Remember that our numbering is alphabetical, so we have to start with bromine. And it doesn't matter if we go clockwise or counterclockwise because the numbering would still be the same for iodine. So bromine is written first with the carbon number indicated, and iodine is written next. So this structure is called 1-bromo-5-iodo-cyclooctane. Let's try naming these 2 cycloalkanes. If there are 2 cycloalkanes bonded to each other, the cycloalkane with more carbons is the parent chain. Naming cycloalkanes as side chains is similar to how alkane groups become alkyl groups when they are side chains. We simply change the suffix from ane to il. So in this first structure, we have a cycloalkane that has 3 carbons attached to another cycloalkane also with 3 carbons. A 3-carbon cycloalkane is cyclopropane. Since both of them have the same number of carbons, it doesn't matter which side becomes the parent chain. We simply change the name of the other cycloalkane to the il form, which is cyclopropyl cyclopropane. Now let's go to the other structure. This cycloalkane has 1, 2, 3, 4, 5, 6 carbons attached to another cycloalkane with 1, 2, 3, 4. Since this one has more carbons, it is our parent chain. A 6-carbon cycloalkane is cyclohexane. And the attached side chain is cyclobutyl. So our first structure is cyclopropyl cyclopropane, and the next one is cyclobutyl cyclohexane. Earlier, we noted that the halogenation of propane produces 2 different compounds depending on which carbon the chlorine attaches to. 1-chloropropane and 2-chloropropane are called constitutional isomers. They have the same molecular formula, but the functional group, in this case the chlorine, is attached to different carbon atoms. Another type of isomerism is stereoisomerism. Stereoisomers have the same molecular formula, the same attachment of functional groups, but with different spatial orientation. Trans and cis are used to describe the arrangements of the attached atoms with respect to the plane of the ring. Cis means that the attached functional groups are on the same side. They are represented by a solid wedge. Trans means that the attached functional groups are on opposite sides and they are represented by a solid wedge and a dashed wedge. Here are examples of stereoisomers. Both of these molecules are cyclohexanes. They both have a bromine atom and a methyl group attached to it. However, one of the molecules have the bromine and the methyl group oriented on the same plane, whereas the other molecule have the bromine and methyl group attached on opposite planes. We denote the first molecule as cis-1,2-bromomethylcyclohexane, whereas the other molecule is trans-1,2-bromomethylcyclohexane. Another example of stereoisomers are these two molecules. They are both cyclopropanes with an iodine and a bromine atom attached. However, this one is trans-1,2-bromoiodocyclopropane, whereas this one is cis-1,2-bromoiodocyclopropane. Note that cis can be represented by lines instead of wedges. And that's it for this lecture. In this lecture, we described alkanes, the simplest hydrocarbons. We practiced naming alkanes using the IUPAC system. We learned how alkanes react with other compounds. We also discussed cycloalkanes, a subtype of alkanes, and we described cis and trans isomerism in cycloalkanes. And that ends Module 10. The deadline for submission of Module 10 activity worksheet will be posted in Google Classroom. Instructions on how to submit the requirements are written in the module. Thank you for listening.